Ladies and gentlemen, this is the fifth lecture in the module of Lean Six Sigma, Measure Phase. During the lecture, Part 2 of the measurement systems analysis will be covered. Repeatability, or variation of the gauge, is calculated using R double bar, or the grand average range, of the repeated measurements across all operators. Using the same gauge, effective operators is averaged out, so as measurements were done with same operator. So we have P operators involved in doing several measurements. Every operator uses the same gauge to measure same parts n times. The standard deviation due to repeatability, gauge variation, is found by measuring each part n times. R1 bar is equal to the average range of trials of m parts by operator 1. R2 bar is equal to the average range of trials of m parts by operator 2. And so on. R double bars is equal to the average of all R bars for all P operators. Sigma repeatability is equal to R double bar divided by D2. D2 is based on n, the number of observations or trials per part made by each operator. You can get it from the table shown. Reproducibility, or operator, appraiser, variation, is calculated using R of x double bar, or the range of grand average, of the repeated trials across all parts. Using the same gauge, effect of parts is averaged out, so as measurements were done on same part. So we have P operators involved in doing several measurements. Every operator uses the same gauge to measure same parts n times. The standard deviation due to repeatability, gauge variation, is found by measuring each part n times. X1 double bar is equal to average of n trial readings made on part 1 by operator P. R of x double bar is equal to maximum x double bar minus minimum x double bar. Sigma reproducibility is equal to R of x double bar divided by D2. D2 is based on P, the number of operators, or appraisers, involved in measurement trials on each part, as shown in table. Assume the following data. 2 operators, each operator will measure each of the 5 parts 3 times, or trials. Please calculate the sigma of repeatability. Please pause the lecture and solve the exercise. Please compare your solution with the solution of the exercise. Assume the following data. 2 operators, each operator will measure each of the 5 parts 3 times, or trials. Please calculate the sigma of reproducibility. Please pause the lecture and solve the exercise. Please compare your solution with the solution of the exercise. An estimate for the standard deviation of the measuring system errors is given by sigma gauge R is equal to the root square of the variance of the repeatability plus the variance of the reproducibility, which is equal to 3.31 in our exercise. Now calculate total observed process variation, which is equal to 15.25. So, the gauge R percent is equal to 21.69%. Now, assume USL is equal to 102 and LSL is equal to 45. Then, by calculating the precision to tolerance ratio, according to its equation, we found that it is equal to 29.88%. Both values are acceptable because they are smaller than 30%. Repeatability and reproducibility are considered as primary causes of measurement error. Gauges and operators are not perfect and produce non-zero errors. A gauge repeatability and reproducibility gauge R&R study involves data collection to assess the total measurement variability, or the variability of the gauge, into two components, while tests and scores the gauge and the operators. The gauge is scored on repeatability. Operators are scored on reproducibility. More than one operator or different conditions are needed to conduct the gauge R&R study. Errors can be modeled by sample standard deviation of all the values recorded based on the summation of variance. Gauge R&R involves in the evaluating the repeatability and reproducibility of a measurement system. Identify the elements of the measurement system, equipment, operators, or data collectors, parts, etc. Select 2 or 3 operators to participate in the study. Identify 5 to 10 items to be measured. Have each operator measures each item 2 to 3 times in random sequence. For example, in manufacturing, a standard would be short form, 2 operators measuring 5 items 2 times; long form, 3 operators measuring 10 items 3 times. Total variation is calculated from appraisers, AV, equipment, EV, for example gauge and part variation, PV. Then total variation is used to determine how much variation is attributable to appraisers and equipment, % R&R. For example, for 3 operators, measure 10 parts 3 times. We will fill in the following table. To analyze the output of gauge R&R, we can bar chart graph for the components of variation. With a good measuring system, value of the part-to-part variation should be larger than the others, because this will be an indication that most of the variation is from true difference in the items being measured. If the gauge R&R, repeat, and reproducibility are larger, this will be an indication that the measurement system is unreliable. A supplier delivers parts with diameter equal to 43.11 millimeters, plus minus 0.13, several times. When you check the batch, you found defective parts. A complaint was raised to the supplier, who in return asked you to check your measuring system. So, you decided to perform an MSA using 3 appraisers. Each will have 3 trials to measure 10 parts. The results are displayed below. As you can see from the data table below, all parts are only off from the target by a few thousandths. No part variation. Diameter is equal to 43.11 millimeters, plus minus 0.13, which means LCL is equal to 42.98, and UCL is equal to 43.24. So, the supplier is right. But what about the measuring system? Please pause the lecture and solve the exercise. The analysis shows that, even though the parts are good, they are too good for the measurement system. But for the measuring system itself, the results are pretty bad. % R&R is equal to 99.88%. It should be less than 10%. Part variation is equal to 4.89%, lesser effect on part variability. Repeatability is equal to 87.07%. Equipment is the main cause of variability. reproducibility is equal to 48.94%, operators also has their effect. Please perform the activity and send your outputs by email for assessment. To access the gauge bias and linearity study template, click Sigma XL, then Measure, then Measurement Systems Analysis, then click Basic MSA Templates, then click Gauge Bias and Linearity Study. Please fill the template of the Gauge Bias and Linearity Study, then click Gauge Linearity Report to generate the report. Here is the Gauge Bias and Linearity Report with all details of the gauge linearity and gauge bias. To access the Gauge R&R Study template, click Sigma XL, then Measure, then Measurement Systems Analysis, then click Basic MSA Templates, then click Gauge R&R Study MSA. Please fill the template of Gauge R&R Study, then click Analyze Gauge R&R to generate the report. In the report, you can see the variance component, total variance percentage, and tolerance percentage for all Gauge R&R metrics, including Gauge R&R, operator, reproducibility, repeatability, part variation, and total variation. To create a blank Gauge R&R worksheet, click Sigma XL, then Measure, then click Measurement Systems Analysis, then click Create Gauge R&R, Crossed, Worksheet. A crossed Gauge R&R study means that every operator or appraiser will measure every part or sample. The default settings are 10 parts, 3 operators, 3 replicates with parts, and operators randomized. Clicking the Reset button will restore the dialog to these default settings. Part and operator names can be edited. Click OK. The following worksheet is produced. Your worksheet order will be different due to the randomization. The results of the Gauge R&R study are entered in the yellow highlighted measurement cells. Click Sigma XL, then Measure, then click Measurement Systems Analysis, then click Analyze Gauge R&R, Crossed. The data worksheet is recognized by Sigma XL and highlighted automatically. Click Next. Select Part, Operator, and Measurement as shown. Check Display Multivary and X-bar, R charts. Check Tolerance Historical Standard Deviation, and enter 8 for the process tolerance upper and lower specification. Click OK. The Gauge R&R study report will be produced. To carry out the analysis in Minitab, choose Stat, then Quality Tools, then click Gauge Study, click Gauge R&R Study. Complete the dialog box as shown. The analysis treats operator, part and gauge. The ANOVA output indicates the part-to-part, gauge-to-gauge variation. The gauge evaluation table also shows the relative importance of each of the sources of variation. Attribute and ordinal measurements often rely on subjective classifications or ratings. For example, rating features as good or bad maintenance services, taste, employee performance, high, medium, low, very low. Kappa is generic coefficient, which indicates several similar measures of agreement for non-quantitative attribute systems. Kappa calculations requires raters, categories and cases, and it calculates a chance measure of agreements between raters. Values of kappa can range from -1 to +1. with -1 disagreement below chance, 0 indicating agreement equal to chance, and 1 indicating perfect agreement above chance. A rule of thumb is that a kappa of 0.7 or above indicates adequate inter-rater agreement. Kappa is typically used in assessing the degree to which two or more ratters, examining the same data, agree when it comes to assigning the data to categories. 5 operators were interviewed separately for a promotional job by a committee consisting of 4 managers of the firm. Suitability for the job is measured on a grade scale as excellent, very good, good, not suitable. Suppose that we have the cases are equal to 5, the number of the operators, and the ratters are equal to 4, the number of the committee, while categories are equal to 4, the number of the grades. Use the table below to enter the data, how the ratters evaluate the employees. In the empty cells, input the number of ratters who agreed that a certain case, or an employee, belongs to a certain category, or a grade. Input a 0 if no ratters agreed that a case belonged to that category. The sum of each row should equal the number of the ratters. Percent of overall agreement, kappa, is equal to 0.267. What do you think is the problem? Again, we will perform the same actions as the last slide, but for different committee. Percent of overall agreement, kappa, is equal to 0.7. What has happened? To access the attribute MSA template, click Sigma XL, then Measurement Templates and Calculators, then click Attribute MSA. Or, click Sigma XL, then Measurement Systems Analysis, then click Attribute MSA, Nominal. Ensure that the entire data table is selected. Click Next. Select Sample Number, Appraiser, Assessed Result, and Expert Reference. Click OK. The Attribute MSA Nominal Analysis Report is produced. The Attribute MSA Nominal Analysis Report include 2 main reports, Attribute Agreement Report and Attribute Effectiveness Report. While this report is quite extensive, a quick assessment of the attribute measurement system can be made by viewing the kappa color highlights. Green indicates for very good agreement, with kappa greater than or equal to 0.9. And yellow indicates for marginally acceptable, improvement should be considered, with kappa from 0.7 to less than 0.9. While red indicates for unacceptable, kappa is less than 0.7. Fleisch kappa statistic is a measure of agreement that is analogous to a correlation coefficient for discrete data. Kappa ranges from -1 to +1. Kappa value of +1 indicates perfect agreement. If kappa is equal to 0, then agreement is the same as would be expected by chance. If kappa is equal to -1, then there is perfect disagreement. To access the gauge study of the attribute using Minitab, choose Stat, then Quality Tools, then the Gauge Study, then click Attribute Gauge Study, Analytic Method. A manufacturing engineer assesses the automated of the attribute of the measurement system that is used for accepting or rejecting bolts. The engineer selects 10 parts that have known reference values and runs each part through a go/no gauge 20 times. The engineer records the number of acceptances for each part. The engineer uses an attribute study of the gauge to assess the bias and repeatability of the measurement system, and to determine whether to improve the measurement system. The system has a lower tolerance of -0.02 and an upper tolerance of 0.02. In part numbers, enter part number. In reference values, enter reference. Under binary attributes select summarized counts, and enter acceptances. In number of trials, enter 20. In attribute, label, leave the default label of acceptance. Under tolerance limit for calculation, select lower limit, and enter -0.020. Click OK. The null hypothesis for the test for bias states that bias is equal to 0. Because the p-value is less than the significance level of 0.05, the decision is to reject the null hypothesis and conclude that the attribute measurement system is likely to have bias. The bias in the attribute gauge system is 0.0099. The engineer should repair or recalibrate the gauge to reduce the bias. Please download from the resources the instructional video for Pareto chart using Excel templates, Sigma XL, and Minitab. Measure phase Sigma XL.mp4, measurement Minitab.mp4, measure phase templates.mp4. Thank you, and see you in the next lecture of the measure phase.